Hi everybody, thanks for watching our video on new work on spatial and immersive audio. In fact, not just new work, but I'll introduce some of the work which has been done over the last decades as well in this talk. But first, let me introduce myself and my company. I might be known from many AES talks about MP3, AAC, audio coding, wave field synthesis and all that. And the company is a startup, just 3 years old, which focuses on solving the old problem of getting good immersive audio reproduction over headphones. And we are around 18 people now, very diverse group of people, some who graduated in Ilmenau, others from all around the world. I don't know how many continents, and we are working together to really solve these old problems and then get this out into the world. So have fun with the following texts and following short videos and have fun. Let me tell you a little bit about current research and what's going on in the world of spatial and immersive audio. And to get there, let me first introduce one very important idea. Early on, when we talked about MP3 and AAC and so on, the human ear was very important, how it works. But for spatial audio, it's really happening in the brain. And to give you for that an example, what's happening in the brain, how expectations have an influence of what we are hearing, let me show you here one example. That was work done at Huddersfield University in England, and you see a vinyl disc. So they let people listen to a vinyl disc and then they switch to an actual audio workstation and ask what sounds better. And 60% of the people said, no, it's a vinyl disc, which sounds better. What these people didn't know was that this looks like a vinyl disc, but it just has a time code on it. And with that time code, it synchronizes playback from the very same source as the other. So people listen to the same, but looking at the vinyl disc, they thought it sounds better. So let's go to the problem of having immersive sound via headphones, binaural listening. We can get great sound via loudspeakers, but using headphones, usually the sound comes from within the head, or we get front-back confusion, or it still does not feel real. So what can be done? People have tried for nearly 50 years now, starting with dummy head recording, which could give you some great effects, but more than that. Then they learned about head-related transfer functions, and we should simulate them in the right way or measure them. So you could have individualized HRTFs being measured, and you can have the HRTFs adapted to your head rotation, so using real-time adapted HRTFs with head tracking. All that works sort of, but only sometimes it works good enough. So you can use room simulation on the signal, or you can do all the above and let people train to listen to these types of signals. But it's still not a solved problem. So what can we do? Let's look into current research on spatial sound via headphones. There are three things very important. First, use the acoustic properties of the actual listening rooms. That's been anecdotal evidence for many years that then it sounded much better. Then use adaptation, learn to listen, training even over long periods of time, and do 6 degrees of freedom tracking so you can move around in the room and listen to the signal. In fact, this moving through a virtual or real scene, that's very important. The interaction with it helps us for orientation tracking. That works already with just rotation. It reduces front-back confusion, or it supports externalization. If we do the full 6 degrees of freedom, together with fast tracking, we get a better understanding of the scene. We can really walk around and get to the different parts of the scene. So that supports the adaptation of the listener, and it might allow a more accurate distance perception. So to summarize, when do we get a plausible spatial auditory illusion? We need a match between our expectations, how a given sound sounds. And that's what the brain remembers. And that includes a number of cues, like for our own anatomy, HRTFs, even individualized HRTFs. But as we have found, this is much less important than most people think. We think we can even do without individualized HRTFs. But we do need cues for the room reflection patterns, visual cues. If we see the sound source, it helps a lot. Proprioception, the feeling for our own body helps, and of course our experience. So for all that, how do we distinguish different types of quality? What are we aiming for? Two major keywords here are authenticity and plausibility. Authenticity means the signal is identically to what we would hear if it would be a real signal. We can switch back and forth. Plausibility means even if we only remember how it should sound, we have the feeling, yes, this could be real. Then we think it's plausible. And for all these, we have built a proof of concept, which we've demoed to more than 600 people by now at AES conventions, conferences, other conferences, and so on. And this has a comparison between real loudspeakers and virtualized loudspeakers. And our rendering in this proof of concept is based on research at TU Ilmenau. People like Annika Neithardt, Stefan Werner, Florian Klein, and others worked a lot on this, did their PhD thesis there. And additional results from other places, including Aalto University and Technische Hochschule Köln. We put all that into our own algorithm we call C3K, work of the last 2 years, and this uses measurements of room impulse responses from real loudspeakers to a reference point, 6 degrees of freedom fast tracking, real-time extrapolations according to the actual listener position, and we use just standard HRTFs from dummy heads like KEMA or KU100s.
Hi everyone, we have presented our demo globally and we received so many questions, and I'm going to answer most of our frequently asked questions. So the first one is about the purpose of our demo and how it can be used in other applications. So the purpose of our demo is to show you that we create an immersive audio that feels like real life, and our demo will bring you to a new level of audio experience. We want to show you that we create a fully three-dimensional soundscape over headphones that replicates the sound of stereo speakers, and it allows you to feel a realistic audio experience as though they are truly present and immersed within the audio content. Our demo system proves that we are able to immerse the listener in a lifelike augmented audio experience. We are further developing our technology to use it in other applications and industry where music or realistic sound is important, such as in music production, AR and VR experiences, gaming, entertainment, leisure, and many more. So for the second most frequently asked question about our demo is, how do we perform our acoustic measurement and what microphone do we use? So for the measurement, we are using an omnidirectional mic, one measurement for each speaker to get reflections of the room, and therefore all other positions are extrapolated from that measurement. We also measure the dimensions of room roughly and give information about the directivity of the speakers into the system. So for the last most frequently asked question about our demo is that what kind of tracking we are using. So for our lab demo, we are using the tracking system of HTC Vive, which is infrared tracking or lighthouses that track the position of the tracker attached to the headphones. It can track the movement of the listener in the room as well as the head rotation. Thus, we have 6 degrees of freedom tracking, and currently we are working on a smarter solution, a tracking solution which will later be shipped to our customers.
Hello, I'm Ulrike Slomer and I work at the edge between technological and business development at Brandenburg Labs, focusing on the perceptive aviation of our technologies. In this workshop, I'm going to present a study we have performed to scientifically confirm our informal success with the doppelganger demo at all the exhibitions and conferences named. The study was also presented and published at DAGA 2023 in Hamburg. A new method of perceptive testing was designed with an approach of a fully blind comparison of dynamic binaural content over headphones with real-placed loudspeakers. The method allows us to evaluate these algorithms as well as the real existing sound source inside the measured room without a visual bias. To achieve this, a LiDAR scan of the listening room was taken without the loudspeakers inside. The scan is presented through the head-mounted display of the HTC Vive, which was also used for tracking purposes during the test conduction. For reproduction, the rear speakers as well as to the side-open headphones were used, such that the loudspeaker signal was lead through with minimized timbral change. The perceptive test was conducted in our laboratory at the Brandenburg Labs office in Ilmenau. The listening room has circa 6 by 6 square meters and a volume of around 115 cubic meters. The loudspeakers were placed at the positions A to E, as seen in the picture beside me. The speakers were oriented towards the listeners, loudspeakers A, C and E, or facing to a window, loudspeaker B, or facing towards a door, which is loudspeaker D. As preparation, we measured the room impulse responses from the 5 loudspeakers placed inside the room with the SDM microphone array from the Technische Universität Ilmenau at the listener position. 2 algorithms were used to calculate the binaural room impulse responses at the measurement position for 360-degree head rotation. A 6 degree of freedom realization could have been done as well, for several reasons. For example, preventing the listeners from running into a loudspeaker, this was not done. The first algorithm, SDM, uses the 6 electret microphones shown and the center microphone to estimate the directions of arrival from the sound field, consisting of a sequence of individual acoustic events. The second algorithm, the algorithm from Brandenburg Labs, is an algorithm which uses parametric extrapolation and solely the measured room impulse response from the center microphone. Further, it takes the geometry of the room as a shoebox model, as well as the positions of the sources and the receiver into account. As audio signal, we used a female voice recording of some parts of the Harvard sentence list. Each loudspeaker was presented for all algorithms and the rear speakers in randomized order, and all was repeated 3 times. For the test conduction, we lead the listener into the room in a way that he could not see the room and the positioned loudspeakers. He was equipped with the head-mounted display, the headphones and the controller for the evaluation and then turned around on his rotatable chair. The listener's task was to place the sound source they hear inside the room using the controller of the HTC Vive. Further, he was asked if he can imagine if the sound he is hearing originates from a real loudspeaker inside the room he sees. This statement should be commented and is used as a measure for the plausibility of the systems on the test. A short training phase was done at the beginning. This was done using the rear speakers to create an inner reference, which was not known by the listeners. In total, 25 listeners took part in our test, but we had to exclude 4 of them from the results. In this plot here you can see the listening room from above with the estimated positions of the heard speakers for all 3 types of reproduction. The red dots show the actual positions of the speakers and the black square the listener position. The method is represented by the different shapes, circle, square and triangle. The colors represent the loudspeaker positions A to E. The filled shapes mark the stimuli which were evaluated as not plausible. To show the differences between the reproduction methods, I switched between them. First, the loudspeakers can be seen. Second, the SDM algorithm. And third, the Brandenburg Labs algorithm. Overall, all was rated fairly similar, but we can observe variations in the distance between listener and estimated sound source as well as in the relative angle. In the following, I am going to show some more details exemplified for two loudspeaker positions A and B. Loudspeaker A was facing towards the listener, loudspeaker B to the window front. The data is mainly not normal distributed, which was tested with the Shapiro-Wilk normality test. The differences were analyzed using non-parametric statistics, namely the Kruskal-Wallis rank sum test with a pairwise Wilkinson rank sum test as post hoc test. Since only a few significant cases without explainable overall pattern were revealed, the significances are not taken directly into account for the further analysis. Here you can see the data plotted as notched box plots with underlying violin plots to visualize the data distribution for the distance from listener position to the estimated sound source position. The distance in centimeter is shown at the y-axis. The solid line represents the actual distance of the real speaker position. The x-axis represents the three reproduction methods. Usually the Brandenburg Labs algorithm is rated a bit nearer, the real source farther away, and the SDM algorithm around the real measured position. Exceptions are the speakers facing away, like seen on the right side, loudspeaker B. Here all methods are rated farther away due to the offset in the estimated angle shown in the following. The now shown plots are similar to the distance plots, except that the y-axis shows the relative angular deviation and the solid line is the actual angle of the real speaker position. The main observation is that loudspeakers facing towards the listener have a smaller angular deviation, around minus to plus 5 degrees. Also, this deviation varies around 0 degree. Loudspeakers facing away show a higher offset, like seen on the right plot, from plus 5 to plus 15 degree for the speaker B in this case. This misplacement is due to the influence of the direct sound and the early reflections reflected from the windows. The next plot shows the plausibility visualized as index. The index is calculated by dividing the number of plausible rated stimuli through the total number of stimuli per condition. The y-axis shows the plausibility index between 0 and 1. The x-axis shows the loudspeaker positions and the methods shaded in different gray. Except for speaker E, no significant differences were found using the chi-squared test. We see the plausibility was rated similar for all reproduction methods. Even the real speakers were similarly often rated as implausible. Verbal feedback gives insight into reasons for plausibility degradation. Our algorithm was told to be more reverberant, which resulted in perceived differences in timbre, source width, or distance localization, for example. This change is caused by the rendering process, where the number of early reflections is reduced to increase runtime performance. Just looking at the resulting indexes, the SDM seems to be rated more often as plausible. The SDM takes more measured information about the distribution of sound into the room into account for the calculation of the binaural room impulse responses for the listener position. With possible movement inside the room, our algorithm would improve in plausibility too. This is because our brain externalizes better with exploration of the acoustical scene. Summarizing, it can be said that there are large deviations between the perceived and the actual loudspeaker positions, regardless of the used aromatization method and even for the actual loudspeakers. Overall, it is well known that localization evaluation in distance and angle is difficult without visual cues. The plausibility was rated similar across all three aromatization methods. The verbal feedback here is important for further improvement of our algorithms. The results indicate that our binaural algorithm is feasible for usage in the most real-life applications. The feedback to our demo at conferences and exhibitions with over 600 listeners has proven that we are able to present a plausible binaural audio illusion with just one measurement taken at the venue.
Brandenburg Labs immersive technology for audio is really exciting. I was very impressed by the demo. It's exciting to see how this technology will develop. I'm looking forward to new immersive listening experiences. And my tip, try it out and test it.
In conclusion, the transformative potential of immersive audio is truly remarkable. We firmly believe that experiencing our cutting-edge technology firsthand is the best way to fully appreciate its capabilities. Whether in our lab or your offices, we welcome the opportunity to provide a demonstration at your convenience. Please do not hesitate to contact us. We will be thrilled to arrange a personalized showcase. Thank you for your attention thus far, and we are happy to showcase our innovative technology to you, and not only at AES conferences and conventions.